Today on Macaulay Math, we're verifying trigonometric identities. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 25 on verifying trigonometric identities. Our goal for today, there's only one. We're going to verify trigonometric identities. This lesson asks students to verify trigonometric identities. The best way to think about verifying trigonometric identities is by realizing that we are just simplifying expressions with algebra, a task that you are all familiar with. The only difference is that now we have some new algebraical rules to use, the fundamental trigonometric identities. This lesson contains little new math, but we will use many old skills in new ways. Let's get started.
Okay, so let's start with some guidelines. And again, this is not an algorithm. You do not follow these step by step by step. These are just some guidelines that give you some tools to help you verify these identities. So let's go through them, and you will see that I am going to use them in different orders at different times. And again, the more practice that you get, the easier that these are going to become. So keep trying. My first guideline is to work with one side at a time, and I would always try the more complex side first. It's always easier to condense than it is to expand. Second, try to factor or add and subtract fractions. If you can pull a greatest common factor out of multiple terms, or if you can add two fractions together to get a single fraction, that can help you to simplify an expression. Try to use the fundamental identities when possible. You may use those in conjunction with this number 4, where you convert all terms to sine and cosine. So for instance, if you've got like a cosecant, you might change that to 1 over sine. And then the last one, just try something. There are a lot of times where you'll try something, it'll come to a dead end, and it may give you some insight as to where you made a mistake, and then you may have to start over, but at least you have a better idea of where you're going. As far as what you need to do to show your work when you're taking a quiz or test, when you're asked to verify a trigonometric identity, you may only use one fundamental identity per step. Since we already know that these problems are identities, it is your job to show each step to get both sides of the equation to be equal. It must also be stated that in many cases, there's going to be more than one correct method to verify these identities. In fact, if you find one that's different than mine, I'm usually pretty fired up about it and will congratulate you. So let's get started, and I will refer back to these guidelines as we work through them. I've got 3 examples. So this first one says verify the trig identity, and right off the bat I'm seeing some squareds here, and squares minus 1, squareds plus 1. So right off the bat I should be thinking, and here I have 1 plus tangent squared theta equals secant squared theta. Well, if I bring this over to the other side, I have secant squared theta minus 1 would be equal to tangent squared theta. Now, the reason that that is a good move in my first step is because I get rid of an addition or a subtraction. So I have cotangent squared y, and then this one becomes tangent squared y, and I want that to be equal to 1. So now I have used one of those fundamental identities to get rid of the subtraction, and already I have only multiplications here. My next step that I see, I have cotangent squared y and tangent squared y. If I go to my trig identity cheat sheet, you'll notice that cotangent theta is equal to 1 over tangent theta. So I can make this 1 over tangent squared y times tangent squared y is equal, and I can make this second one into a fraction, and when you're multiplying fractions you can cancel along the diagonals, so these two tangent squareds cancel. 1 times 1 is 1, and we are finished verifying that identity because we've got the left hand side and the right hand side being equal to each other. Next example, this one's a little bit more complex, and when I decide which side of the equation to work on, clearly this side is a little bit more complex. I notice that I have a cosecant here in the top and a sine here in the bottom. I know that cosecant theta is equal to 1 over the sine of theta. So I'm going to change that first. So I'm going to go 1 over the sine of x minus 1 all over 1 minus sine x. All right, the next thing that I want to do here is I am going to want to try and make a single fraction here in the numerator. So I am going to say that 1 is equal to the sine of x over the sine of x. And I will rewrite this as 1 over the sine of x minus sine x over sine x. And that will all be over 1 minus sine x. Now the reason I did that is because now I can combine this thing into a single fraction. And that single fraction is 1 minus sine x all over sine x all over 1 minus sine x. Since these two fractions have common denominators, I can simplify them into a single fraction. All right, so I can here add fractions. Since these two fractions have common denominators, I can condense them into a single fraction. Now, when I look at this expression here, I have 1 minus sine x and then another 1 minus sine x. And again, I can change this into a fraction. And I'll put that all over 1. And so I have this fraction right here, 1 minus sine x over sine x. That's in the numerator of this big fraction. And in the denominator of the big fraction, I have this second smaller fraction of 1 minus sine x all over 1. And so if you have a over b all over c over d, I am dividing fractions here. And what that'll allow me to do is multiply by the reciprocal of the bottom fraction. And that's just what I'm going to do. So I'm going to take this top fraction right here, and I'll make it 1 minus sine x all over sine x. And then I will multiply by the reciprocal of what's on the bottom here. So the 1 goes on the top, the 1 minus sine x goes on the bottom. And just like in the last example, I can cancel along the diagonal. Those are the same terms, so they'll factor out. That will leave me with 1 over sine x. And this is fairly simple, so let's go back up and say, what am I trying to get this to equal to? I'm trying to get it to equal to cosecant x, and I know that 1 over sine theta is equal to cosecant theta, so in this last step, I can say that this is cosecant x. Last example, it says verify the identity. Now we've got a lot of these secant to power, secant to a power, another secant to an odd power, a tangent to an odd power. So I've got a lot of stuff going on here. And since I have even power, you might think that it's a good idea to start looking at your Pythagorean identities. And that may work, but I've already done one that uses a Pythagorean identity. And I'll notice here that I have a subtraction, and this first term and this second term of the subtraction has a lot in common. And so what I think I'm going to do here is I think I'm going to factor a GCF from both terms. And that GCF, so what's the biggest thing I can divide out of both of these? Well, what's inside the parentheses is the same, so I can divide that out. I have a secant to the 6th x and a secant to the 4th x. And so the greatest common factor between these two parts is going to be secant to the 4th x. So if I divide out a secant to the fourth x and a secant x tangent x from both terms, that will cancel that out, and that'll cancel 4 of these 6 secant x's. So that will leave me with secant squared x. And since my greatest common factor is secant to the fourth x, secant x, tangent x, when I divide this expression into that expression, I'm basically dividing everything out. So just like 5 divided by 5 is 1, secant to the fourth x times secant x tangent x is also just 1. Now I see that I have another secant squared x minus 1 here. So I have this minus 1. And again, if I go back to my trig identity cheat sheet and look at my Pythagorean identities, secant squared theta minus 1 is tangent squared theta. So I can come back down here. Now that leaves me with this secant to the fourth x, secant x, tangent x, and then I can replace this expression with tangent squared x. Now I think that that's a good move because, again, we always should be referring back to what we're trying to get to. This expression had a subtraction in it. By using the Pythagorean identity, I only have multiplications, and there's no subtraction in either my left-hand side or my right-hand side. Now I can simplify here. I only have multiplications. Secant to the fourth x times secant x will be secant to the fifth x. Tangent x times tangent squared x will be tangent to the third x. There's nothing else that I can simplify here, and it looks like what I was asked to verify, so I am done. All right, that is all I got for today, folks. So, the Star Wars fun fact of the day: Steven Spielberg's creation, E.T., the extraterrestrial. This species makes a cameo in the Senate scene from The Phantom Menace, Episode 1, and you can see them right here. Well, that's all I got for today, folks. Have a great day. Goodbye.